Good morning. In the last video, we have studied the scalar triple product and its geometrical interpretation. When we evaluate the product of three vectors and if it works out to be a scalar quantity, such type of product of three vectors is called as scalar triple product. And we have seen that it is defined as A bar dot B bar cross C bar. B bar cross C bar is a vector, and if we take the dot product of this vector B bar cross C bar with the given vector A bar, then it results into a scalar quantity, and that is why such a product is called as scalar triple product. Again, if we evaluate the product of three vectors in such a way that if the result of multiplication of three vectors works out to be a vector quantity, such product is called as vector triple product. So today we are going to study what is this vector triple product and its proof. So for that purpose, let us consider we have the three vectors starting from the common point O. This is the vector A bar, this is the vector B bar, and this is the vector C bar. Here the vector triple product of the three vectors A bar, B bar and C bar is expressed as this product should be expressed in such a way that the result of multiplication of the three vectors should result into a vector quantity. So first, if we take the cross product of B bar and C bar, it will result into a vector quantity, and if again we take the cross product of A bar with the vector B bar cross C bar, then the result of multiplication of these three vectors will result into a vector quantity, and hence this type of product of the three vectors is called as vector triple product. So the vector triple product of the three given vectors A bar, B bar and C bar is expressed like this. Now, when we evaluate the cross product of B bar and C bar, this vector B bar cross C bar will be perpendicular to the plane of B bar and C bar. So in this diagram, this plane PQRS is the plane of B bar and C bar. So when we evaluate this cross product B bar cross C bar will be perpendicular to the plane of B bar and C bar. So it will be perpendicular to the plane PQRS. Now when we take the cross product of B bar cross C bar with A bar, this vector A bar cross B bar cross C bar will be perpendicular to the plane of A bar and B bar cross C bar. So this plane LMNO represents the plane of A bar and B bar cross C bar, so that the vector A bar cross B bar cross C bar will be perpendicular to this plane LMNO. And as we observe here that since the vector B bar cross C bar is perpendicular to the plane of B bar and C bar, that is perpendicular to the plane PQRS, and the plane of A bar and B bar cross C bar is naturally perpendicular to the plane PQRS. So when we evaluate the cross product of A bar with B bar cross C bar, this resultant vector will be again perpendicular to the plane LMNO, so that this vector A bar cross B bar cross C bar will lie in the plane PQRS itself, and this plane PQRS is nothing but the plane formed by the vectors B bar and C bar, and these two vectors B bar and C bar here are going to lie on the parenthesis. So when we evaluate the cross product, vector triple product of the three vectors A bar, B bar and C bar, then this vector triple product will lie in the plane of the two vectors in the parenthesis, right? Okay. So that is how we define the vector triple product of the three given vectors. Now, from this what we can conclude is that if this vector A bar cross B bar cross C bar lies in the plane of B bar and C bar, this lies in the plane of B bar and C bar. So, if we maintain the cyclic order of the vectors, this vector triple product again can be expressed as B bar cross C bar cross A bar. So, what we will observe here? This vector triple product will lie in the plane of C bar and A bar. As well, the vector triple product C bar cross A bar cross B bar will lie in the plane of A bar and B bar. So, what can we say about these three vector triple products? In case of scalar triple product, we have seen that A bar dot B bar cross C bar is equal to B bar dot C bar cross A bar is equal to C bar dot A bar cross B bar. If the cyclic order of the vectors is maintained, the scalar triple product remains C. On the similar lines, can we say in case of this vector triple product, these three vector triple products will be equal? So, A bar cross B bar cross C bar, B bar cross C bar cross A bar, and C bar cross A bar cross B bar. So, can I put equality sign here? Cannot be. Why? The reason is that this first vector triple product A bar cross B bar cross C bar lies in the plane of B bar and C bar. The second vector triple product B bar cross C bar cross E bar lies in the plane of A bar, C bar and A bar, and the vector triple product C bar cross A bar cross B bar lies in the plane of A bar and B bar. So, these three vectors which lie in the three different planes cannot be equal. Cannot be equal. So, what we can write here is the inequality sign. So, we should put here the inequality sign. So, this vector triple product A bar cross B bar cross C bar will not be equal to B bar cross C bar cross A bar, and again it will not be equal to C bar cross A bar cross B bar. Right? Okay. So, that is the first conclusion that we can draw from this vector triple product. The second conclusion we can draw is that in case of the scalar triple product, we have seen that the scalar triple product of the three vectors is expressed as A bar dot B bar cross C bar, and we have seen that one of the characteristics of this scalar triple product we have seen is that the positions of dot and cross can be interchanged, so that the scalar triple product remains unchanged. So, if we interchange the position positions of dot and cross here, we can express this product as A bar cross B bar dot C bar. So, by interchanging the positions of dot and cross, the scalar triple product remains unchanged. On the similar lines, can we say here that A bar cross B bar cross C bar will be same as A bar cross B bar cross C bar. Can I put equality sign here on the similar lines as we observe in case of scalar triple product? So can I put equality sign here? Cannot be. Why? The reason is again the same one. The first vector A bar cross B bar cross C bar lies in the plane of B bar and C bar, whereas this vector A bar cross B bar cross C bar lies in the plane of A bar and B bar. So these two vectors lie in the different planes, so these two vector triple products will not be seen. So we should put inequality sign here. So these are the two conclusions that we can draw from the vector triple product. So that is the vector triple product and its conclusions. We can express the vector triple product for the unit vectors. So in case of unit vectors, how can we evaluate the vector triple product? Let us see. So for that purpose, let us consider we have the vector A bar is equal to I cap, B bar is equal to again I cap, and C bar is equal to J cap. So using these values of A, B, C here, what we get? We'll get A bar. A bar is nothing but I cap cross. B bar is nothing but I cap cross. C bar is nothing but J cap. So what will be this vector triple product of the unit vectors? So I cross C. So this is nothing but equal to. What will be I cross J? I cross J is nothing but K. So this is I cross K. And I cross K is equal to minus J. So this is the vector triple product of the unit vectors. Now, if we interchange the position of this parenthesis, so what will be I cross J? I cross I is 0. So, and if I cross I is equal to 0, then this vector triple product will be equal to 0. So, if we change the position of the parenthesis, the vector triple product is not seen or is not equal. Right? So, that is about this vector triple product. We can define this vector triple product as A bar cross B bar cross C bar, or by changing the three vectors in cyclic order, we can express this vector triple product in these three different forms. But here, one point we should remember is that these three vector triple products are not equal. They are not equal. Okay. Next, we shall see is the proof of the vector triple product. So here, what we observe is that the vector triple product of the three vectors A bar cross B bar cross C bar. Say, since it is a vector, let us represent this vector by another vector, say D bar. Say D bar represents the vector triple product of the three given vectors A bar, B bar and C bar expressed like this. We have seen here that this vector D bar or the vector A bar cross B bar cross C bar lies in the plane of the two vectors in the parenthesis. This vector A bar cross B bar cross C bar lies in the plane of the two vectors in the parenthesis. So what we can say is that we can express this vector D bar in terms of the components of the two vectors. So this vector D bar can be expressed as A B bar plus B C bar, where A is the component of D bar in the direction of B bar and B is the magnitude of the component of D bar in the direction of C bar. So this is just like the resolution of the vector. So this vector D bar can be expressed as A B bar plus B C bar because this vector D bar lies in the plane of B bar and C bar. So what we can write here is that now this vector D bar, suppose this is the vector D bar. This vector D bar is going to be perpendicular to the vector A bar because we have said that this plane PQRS and the plane LMNO are perpendicular to each other. These two planes are perpendicular to each other. And if these two planes are perpendicular to each other and the vector D bar, that is A bar cross B bar cross C bar, lies in the plane of B bar and C bar, that is in the plane PQRS, and the vector A bar lies in the plane LMNO. So the two vectors A bar and D bar are mutually perpendicular to each other, and if the vectors A bar and D bar are mutually perpendicular to each other, what we can write is the most important property that we have studied for the dot product of two vectors, that if the two vectors are perpendicular to each other, then their dot product is equal to 0. So since A bar and D bar are perpendicular to each other, since A bar and D bar are perpendicular to each other, the dot product of A bar and D bar must be equal to 0. So using this expression for D bar here, we can write this expression as A bar dot into bracket A B bar plus B C bar, and this is equal to 0. So if we open up this bracket, we can express this relation as A into bracket A bar dot B bar plus B into bracket A bar dot C bar is equal to 0. Or if we transfer one term to the right hand side, we can express it as A into A bar dot B bar is equal to minus of B into bracket A bar dot C bar. Or transferring these brackets to the opposite sides, we can express this relation as A upon A bar dot C bar is equal to minus B upon A bar dot B bar. So this ratio remains constant, and this ratio, this constant, is say equal to P. Suppose this ratio is equal to P, a constant. The value of this constant can be obtained. How? That we'll see later. Now, if we consider this first term and the last term on the right, A upon A bar dot C bar is equal to B. We can express A in terms of P and A bar dot C bar. So, by considering this equality, we can write A is equal to P into bracket A bar dot C bar. Similarly, considering this second equality here, we can write B is equal to minus P into bracket A bar dot B. So, using these values of the constants A and B, here A and B are the real numbers. A and B are the real numbers. So, using these values of A and B in this expression, what we'll get? We'll get A bar cross B bar cross C bar is equal to A B bar plus B C bar. So this is good. Using the value of A as P into A bar cross C bar, this is P into A bar dot C bar into B bar plus B is to be replaced by minus P into A bar dot B bar. So this will be minus here, minus P A bar dot B bar into C bar. So P is common in the two terms, so we can take it outside the bracket, and in the bracket it is B. Okay. This is A bar dot C bar into B bar minus A bar dot B bar into C bar. We can find out the value of this P by using the appropriate values for the vectors A bar and B bar and C bar. By considering the appropriate unit vectors for A bar, B bar and C bar, we can write. So here, let us consider, let A bar is equal to phi cap, B bar is equal to phi cap, and C bar is equal to J cap. So let us consider A bar is equal to I cap, B bar is equal to J cap, and C bar is equal to B bar is equal to I cap, and C bar is equal to J. So using these expressions for A, B, and C, in this expression, what we will get? We will get this A bar is to be replaced by I cap, so it is I cap cross. B is to be replaced by I cap and C is to be replaced by J cap. So this is equal to P into bracket A dot C. A is I cap and C is J cap into B. B is I cap minus A bar dot B bar. A is I cap dot B is again I cap into C bar is J cap. So that is what we get. So this is I cross J is K, I cross J is K, and I cross K is minus J. So this is equal to minus J is equal to P into bracket. I dot j is 0, 0 minus I dot I is 1, so this is j cap. So minus j cap is equal to minus pj cap. So this implies p is equal to 1. This implies p is equal to 1. So using this value of p in this expression, we get, substituting p by 1, we get therefore a bar cross b bar cross c bar is equal to a bar dot c bar into b bar minus a bar dot b bar into c bar. So this is how we can prove the vector triple product of the three vectors a bar, b bar and c bar, as a bar cross b bar cross c bar is equal to a bar dot c bar into b bar minus a bar dot b bar into c bar. Or the same expression can as well be expressed as a bar cross b bar cross c bar is equal to b bar into a bar dot c bar minus c bar into a bar dot b bar. So this is more convenient to remember because this is nothing but equal to BAC minus CAB back cap. So a bar cross b bar cross c bar is nothing but equal to b into a bar dot c bar minus c into a bar dot b bar. So this is more easy to remember, back cap, back cap. So this vector triple product is also sometimes called as back cap rule. This vector triple product is sometimes also called as back cap. So this is how we can express the vector triple product of the three given vectors a bar, b bar and c bar. So this proof of the vector triple product also can be obtained by expressing the three given vectors a bar, b bar and c bar in terms of their rectangular components also. A bar is expressed as I cap ax plus j cap ay plus k cap az. B bar is expressed as I cap bx plus j cap by plus k cap bz, and C bar is expressed as I cap cx plus j cap cy plus k cap cz, and replacing these vectors by their rectangular components, also we get the same expression for vector triple product of the three vectors a bar, b bar and c bar, so that you can try on your own. Okay, so that is all about this vector triple product, and we will come to the end of this chapter on vector analysis. So in the next video we shall try to attempt some problems from this chapter. Okay, thank you.